we discuss electric field in this lecture. Michael Faraday is the first to bring up the concept of electric field. What is an electric field? Electric field exists in the region of space around the charged object. If we put another charged object, let's call it test charge, at the location close to another charged particle, the field at the location that the test charge is at will exert a force on that testing charge. Now, there are a few things we want to clarify. Electric field is a physical quantity. It's a field quantity, which means it has a value at each point in space and time. And also, electric field is a vector quantity. A vector means it has a magnitude, it has direction. Now, electric field also has dimension, aka unit. And also, contrary to a lot of people's misunderstanding, electric field is a matter. It can carry energy and momentum. Even though it's invisible, it's a matter that is as real as anything that we know of, like the book, like the computer that you're watching this video from. So just like the computer, electric field is a matter. It carries energy and momentum, and it exists at every point in space. In this example, the charge Q, we write capital Q, will create an electric field around it. Now, this electric field exists at almost all points surrounding this capital Q charge. And then we put a test charge, let's call it Q naught, at a location which is close to this capital charge, capital Q. From Coulomb's law, we know there is going to be a force acting on this Q naught, pointing to the right. And we see there is an electric field pointing to the right at the location of charge Q naught. The definition of electric field is given by the electric force received by this test charge Q naught divided by the charge of this testing charge Q naught. Because force unit is Newton, charge of Q naught is Coulomb, so the unit for electric field is Newton per Coulomb. That's the definition of electric field. And this is a vector equation, which also means the direction of electric field is the same as the force, is the same as the direction of the force acting on the testing charge Q naught. But this is a little bit subtle. Please remember, we see electric field has the same direction as the electric force on test charge only for positive testing charge. If we have a negative charge, it will create electric field directed toward the negative charge. If we put a positive test charge at location A, the force on this positive testing charge would be pointing to that negative charge, which is consistent with our knowledge of Coulomb's law that a positive and a negative charge attract each other. If we have a positive charge, it will produce electric field pointing away from the positive charge. If we put a positive test charge at this location, the force on the test charge would be pointing away from the positive source charge, which is again consistent with Coulomb's law. like charges repel each other. When we test the electric field using a test charge, it's important to remember it has to be a small charge so it doesn't change the charge distribution on the source charge. And the electric field at that location produced by the source charge exists regardless whether you put the test charge at that location or you don't put the test charge at the location. You always have electric field as long as you have source charge. Just like electric force, electric field also satisfies superposition principle. In this example, we have charge Q1 and Q2. Charge Q1 will create electric field E1 at position P. Charge Q2 will create electric field E2 at position P. The total electric field at position P would be the sum of E1 and E2. Now again, remember, E1 and E2, they are all electric field, so they are all vectors. If we want to add two vectors, we have to do vector sum.
An electric field is a disturbance in space created by the presence of electric charge. The electric field at a particular point in space can be defined as the force per charge on a test charge at that point in space. For a single positive source charge as shown, the force and hence the electric field depend upon the position of the test charge. The field exists at every point in space regardless of whether there is a test charge there to sense it. An array of vectors can help visualize the field. These field vectors reflect the symmetry of the charge. In this case, they show the field is directed radially outward from the positive source charge. For a single negative source charge, the force in the positive test charge is attractive. As a result, the force, and hence the electric field, will now be radially inward. As was the case for the single positive source charge, the field resulting from a negative source charge is spherically symmetric.